Hello, everyone. I'm sorry I can't be with you. I'm recovering from pneumonia, and I'm also sorry I won't be in top form, but I'll do my best. I'd like to talk about getting maximal functionality from simple grippers. All right, you all know about gel site. You can get these wonderful signals from it. And these days, we want to figure out how to use those signals in the context of getting training data, in particular with doing teleop for training data. And so that's what I'll talk about. So we want to, first of all, demonstrate that tactile sensing has utility in manipulation. We want to figure out how to incorporate our sensors into teleop systems so we can gather the training data. And for the sensors and the manipulators, we want to improve the usability and the durability. Those are a variety of challenges we have. Let me start with PolyTouch. This is a system developed in collaboration with Toyota Research Institute. TRI has a big program gathering data with professionally trained operators working in a data generating factory, basically. The challenge here was, how can we build a robust and widely useful gripper that incorporates tactile sensing, gel site style. And what we end up with is it's a parallel jaw gripper. It's got two halves. On one half is the fin ray, which is traditionally used in a lot of TRI's grippers, and the other half is sort of a mirror fit to the fin ray, but which is equipped with sensing, and it's not just tactile sensing, but also visual sensing and also acoustic sensing from a contact microphone. And all of that we can fit into a single data stream in an HDMI cable. So anyway, we got these three modalities in a cable. If you look in the middle, you can see the fin ray and the gel site style sensor opposed to each other. They're grasping an object there, which is a pair of metal tongs. And on the right, you see the camera view. There's a camera in there, bouncing off a mirror. Down the middle is this colorful strip, which is the gel site signal. And off to the sides are two windows. The camera is wide angle enough that it looks at this strip, but it also sees what's happening to the sides of the strip. And what's happening to the sides gives you peripheral vision of the scene, basically. And in addition to that, there's a contact microphone on there to give an acoustic signal. The acoustic signal tells you about contact events, and it also has vibration sensing for slip and so on. And one of the requirements here was to make something that was robust. As you may know, the commercial sensors you buy from Gel Site Inc. are not very robust. They tend to break with a rather appallingly low amount of wear. And so one of the challenges here was to make something that was, first of all, much more robust than that. Secondly, something that everyone can make using stuff you can buy on Amazon. And all the instructions are available for anybody who wants to do that. Anyway, we find that we don't have the high resolution that you get with the commercial sensors, but much greater durability, plus it's something that you can make and repair yourself. So those are great advantages. And here it is in action. On the top is what we get with vision only. This is after training with this teleop data. And the point here is just that it screws up. This is just one example. And on the bottom is what happens when you've got the Polytouch data included. They're both trained from the same data, except with or without including the Polytouch information. And you wouldn't think of this as a particularly tactile task, but it turns out the tactile information and the acoustic information are actually quite useful in making this successful. Now I'd like to talk about something that's it's not out yet. It's going to be presented at IROS 2025. And this is the Grasp Everything Gripper, or Get Gripper. And this is, it's a very simple gripper, solving a problem that I think is quite important, although people aren't always thinking about it. And the problem is the fragility of grasps that you get out of parallel jaw grippers, typically. All right, so two jaw grippers, or parallel jaw, or angular jaw, whatever. They're very popular. Everyone loves them and hates them. What's to love? Well, they're simple and easy to control. Hate one is that they're not dexterous, and we're not going to do anything about that right now. But hate two is that they have fragile grasps. You start out with a grasp that seems like you've got a good grasp, but you bump into something, or it wiggles, and the grasp lets loose. So let's analyze why that happens. Why are two-jaw grippers bad at grasping? Well, they make antipodal grasps. That's a famous classic grasp. Everybody seems to think it's okay. But it's inherently fragile. You've got two opposed contact patches. You've got 1 degree of freedom, which is constrained by normal force on either side. You've got 4 degrees of freedom that are well constrained by friction, and 1 degree of freedom that is poorly constrained by friction. It's this rotational degree of freedom, that's rotation about the axis between the contact patches. So what happens is the object starts to rotate because it got bumped, or you wobbled it, or something like that. That rotation converts the static friction into kinetic friction, which is much lower than the static friction, and so the thing lets loose and it goes crashing. And that's a very common failure in two-jaw grippers. And so what could you do about that? Well, if you just look at the problem is you only had 5 good constraints and you need 6, so you can just add an extra finger and you'll get 6. In this case, these 3 fingers will give you 1 constraint from normal force and 5 from friction, good ones from friction. So, should we just use a 3-jaw gripper like one of these commercial ones? There's the Canova gripper. It's under-actuated, has 3 actuators, 6 total degrees of freedom. There's the Robotique. It's got 3 fingers, under-actuated. It's got 4 actuators and 10 total degrees of freedom. And so what happened? We were playing with these one-off grippers, and all of a sudden we're up to these very complicated grippers. Do we really need to do that just to get our 3 fingers? And no, we don't. We can get 3 fingers with just with a 2-jaw gripper. A one-doff gripper, just like we had before, except instead of having 2 fingers opposing each other, we have a pair of fingers opposing 1 finger. So we have 2 against 1 grip here. 2 fingers on one side, 1 finger on the other side, and so we got 3 contact patches, and we've got a nice stable grasp. And in general, 2-point contacts are going to give you a bad grasp, and 3 are going to give you a good grasp. Okay, but there's a problem, which is that small objects are going to slip between those 2 fingers. So how do we make this multi-scale? Well, we could just turn those fingers into, let's say, cones or some other tapered shape. On one side, we've got a split finger On the other side, we've got a single finger, and on both sides, they are tapering and converging in a self-similar way, so we can grasp small objects near the tips, large objects near the base. And here's what we actually end up with. This is the components of a gripper designed to be used on the Aloha system. On the left, you see the split finger looks like a triangle because we filled in the cross piece. We also have fingernails to help us pick up small objects. And on the right, you see the multiple components. We've got a rigid backing and these tapered elastomeric pads. And on the right side, we're actually looking through. We've made it clear so we can look through it with the camera. So we can use this nice stable grasper, and we can get gel sight style data from our camera, which is looking at the back of one of the fingers. And here's the gripper in operation. This is being teleoped on the Aloha, and we're getting some peanut butter. And this round-handled butter knife is very unstable in an ordinary gripper, almost impossible to control. But with this, with our gripper, we can get good control on it. All right, so we did some experiments where we had people teleoping on the Aloha, and well, the answer is simple. We've got these three kinds of grippers, always in a parallel jaw gripper on the Aloha. The Get gripper, or the classic Aloha grippers that normally come with it, or we just made simple flat-fingered parallel jaw grippers and compared them, and the answer is, especially look on the right with the blue lines, that shows when you're grasping large objects and they are subject to a disturbing force, how well are you able to keep control of the object, and the light blue lines show that the Get gripper always does better than everybody else. So that's what we've done so far. We haven't, we've demonstrated the utility for getting more stable grasps in a context like use on the Aloha. And our next plan is to use this to gather training data and to build autonomous manipulation. All right, now let's talk about a fancier hand. This is the eyesight hand. We're trying to get some dexterity now, but it's as simple a hand as we can build and still get the dexterity we need. So we're inspired by the human hand. We're basically replicating the kinematics of a human hand. And we observe that humans can do almost everything they need to with 3 fingers. So let's build a hand with 3 fingers, but as simple as possible. We put tactile sensing everywhere, and we also built in direct drive motors so as to make the thing compliant and robust to collisions. So here's the gel sight sensor. Actually, all of the finger pads and the palm have gel sight sensing on them. The palm has 2 cameras, and each of the finger pads, both on the fingertip and the phalanges, have a camera each. And this is an early version where the hand was teleoped with electromagnetic sensors built into a glove. And it's pretty good, but later you'll see that we've switched to a different teleop system. This is a version that was 6 DOFs, but we've also done 7 DOFs and 9 DOFs. And this is showing one of the most important things, which is that your hand should be robust to collisions and not be fragile and break when you bump into things. That's surprisingly difficult to do and requires careful design of your motors and gearing. Okay, so now we're positioned to do some training. We've got a lot of data coming in. We've got the basically it's all cameras. We've got 2 vision cameras, 1 global camera and 1 wrist camera, and we've got 8 cameras in the tactile sensors. Now the operator is not getting any feedback from the tactile sensors, and with these electromagnetic sensors, also not getting proprioceptive feedback. But the policy is able to get that information and use it. So even though the operator isn't getting it directly, it's still available in training the policy. And here's a comparison between what we get with the policy we get when we include the tactile data on the left, and what happens if we don't have it on the right. So this is a tricky task. You have to get your finger against that little lip there, and when you've got enough pressure, pry it up. And if you only have vision, well, you just can't tell when that's happened, so you miss it. Likewise here, when you're picking up this plate, if you've got the tactile data on the left, you can tell whether or not you've got a good grip. By you here, I'm referring to the robot, because these are autonomous. This and the bottle opening are autonomous. Anyway, so if you've got that data, you can get a good grip and know you've got a good grip. And if you don't have it, you're confused because the vision just doesn't contain enough information. Okay, now the teleop is it's not fun to do because you don't feel like you're really in contact. It feels very unnatural. And so we've been exploring a different approach to teleop using an exoskeleton. And so this picture on the left shows the Dexop. That's an exoskeleton which is just mechanical. It's passive and mechanical. It replicates the kinematics of the eyesight hand and feeds it to the human hand. And because it's mechanical and passive, there's no latency, and you get proprioceptive feedback. You still don't get cutaneous feedback, unfortunately, but you do get the proprioceptive feedback, which is very important. And it feels more natural and direct, and it's fun to use instead of being frustrating. And here is Haoshu opening a box, and inside the box is another box. They're tucking everything away. Very nice. Okay, now there's a little box. Now let's open that box, and inside that box is a bag. And well, we can keep going, but let's stop there. The important point here is this is a very natural feeling task, and you can do remarkably dexterous things once you get the hang of it. So it's a great way of gathering training data. Here it is again being teleoped directly with these linkages to do a challenging task, which is open this little bag and get the washers out. There we go. Let's pour out the washers. Very good. And then a couple of tasks involving power grasps, but not just dumb power grasps, but power grasps that include a certain amount of dexterity. On the left is the iron, and on the right is is grasping a squirt bottle for cleaning a whiteboard, and it involves a power grasp plus this dexterous use of the thumb. All right, here's Haoshu showing off his two hands and what he can do with them, and he's going to do a very simple task, which is screwing in a light bulb, or a pretend light bulb. Anyway, so there's the light bulb, and there he is screwing it in. Very good. And he's not rotating his wrist. All the rotation is being done with the fingers, with the three fingers, with a dexterous movement. And here's the robot having learned by imitating what Haoshu was doing. It's not quite as dexterous as Haoshu, but it's pretty good. And it's doing this three-fingered movement in order to do the screwing. And again, it's making use of all the vision data and the tactile data in order to achieve this. All right, so let me summarize. Of course, we want to use tactile data for everything we can, and these days, one of the main things is to do teleop and train robots. So I've told you about several projects we have on that. First of all, PolyTouch. That's a tactile plus vision plus sound. The vision and touch is from one camera plus a contact microphone. And that's designed not only to be useful, but to be robust and easy to build so that you can gather lots of data without having the thing fall apart. The gut gripper solves a persistent problem with two-jaw grippers, which is that the grasps tend to be fragile. So we have split fingers, plus we have gel site sensing on it. And we've implemented on the Aloha system and demonstrated that it's good for teleop, and soon we'll demonstrate that it's good for training. The eyesight hand has three sensorized dexterous fingers, plus a palm, which is also sensorized. It's built with robust direct drive motors, and we can drive it either with a classic type of glove-driven teleop, or with this new Dexop, this exoskeleton that uses linkages, which has the advantage that it gives you much better dexterity, proprioceptive feedback, plus it's more fun to use. And that's it. Thank you very much.